Hello everyone. In this video, I'm going to introduce the field of mathematics called graph theory through its origin story. So before we get into the origin story, first we're just going to define what we mean by a graph. So this won't be the rigorous definition that we deal with later, but we can think of it as a collection of vertices and edges between these vertices. So we'll give a few examples here. So by vertices, I just mean like nodes or points. So one would be something like this. So there doesn't have to be an edge between every pair of vertices, right? This one has one disconnected vertex over here. Another example, we could have them all be connected. So a triangle here would be a graph. You can have multiple edges between 2 points. You don't have to just have one at most. You can also have loops. So we could have a graph like this one, where there's a loop at a point. So just an edge from a vertex back to itself. So all of these four pictures here represent different graphs. And in general, we're going to see that graphs can be used to model a lot of real life situations and are a really useful mathematical tool. So now let's talk about how people kind of first came up with these and why. So the origin story dates back to the 1700s and a famous problem called the Seven Bridges of Konigsberg. So this was a city in Prussia. Again, this is in the 1700s. Prussia no longer exists. It's now Kaliningrad, Russia. And it was a city that was built along the Pregel River. And so we're going to draw a picture here. So we had land masses on either side of this river and a couple of islands as well. So we're going to label these A, B, C, and D. And then, well, as you might imagine from the name, there were 7 bridges here. Okay, so we had 2 going from A over to C. We had 2 more going from A to the other side of the river. There's one bridge between the 2 islands, and then from this island on the right, there is a bridge to either side of the river. And so we're going to see here in a second how we translate this into a graph. And so I'm actually going to number these bridges. I'm just going to go clockwise here. So 1, 2, 3, 4, 5, 6, and 7. And so the actual problem was as follows. So the people of the city wanted to know, is there a walk that one can take through the city that crosses each of these 7 bridges exactly one time? Okay, and there are a lot of different options, right? I mean, you could start on either of the islands, on either side of the river, and then you have a whole bunch of different orders you could take in terms of the bridges. And so, I mean, you definitely don't want to try this by foot or you're going to get really tired. So it turned out that a famous mathematician, Leonard Euler, who is Swiss, was actually able to turn this into a graph theory problem and solve it. So let's talk about Euler's way of looking at this. So looking at this picture, Euler said, well, it doesn't really matter where we are on the land. It's more the bridges that connect the pieces. And so he just collapsed each of these land masses to a vertex, as he started to create a graph. So he had a vertex for A, vertex for C, vertex for D, and a vertex for B. And then he had edges representing the bridges that would connect each one, right? So there were 2 edges from A to C, which this is why we labeled these up above. So these were like 1 and 2, right? There was one from C to D. That was 3. From B to D, 4. There was one from A to D. That was 5. And then there were 2 more from A to B, right? Edges 6 and 7 up on the picture. And so the general layout of the city, he just put into vertices and edges between them. Okay, so then how can we actually start using math and not just, okay, cool, we drew another picture, it's slightly simpler than before, but how does this actually help us solve a problem? So we can start by just trying to do an example and see like what it would look like to take a walk and try to cross all these bridges exactly once. Right, so that means we want to travel along these edges and not use any edge twice, right? So let's say we start at A. Okay, and then maybe we travel to C. We're going to try to use every edge once. So in this one, I'm going to go back to A. Then I'll go forward to B. Maybe back to A again. And then to D. But then I have an issue here, right? Because no matter if I go up to C or down to B, I'm not going to be able to get to the other side, right? I would have to reuse a bridge. And so this way definitely doesn't work. And we actually have notation for what we just did. We don't have to like remember all of these. This is what we call, and again, this kind of dates back to what Euler was talking about. This is called a walk. And so here it's just a sequence of vertices and edges. So we started at A, then we went edge 1 to C, then we went edge 2 back to A, then we went edge 7 to B, edge 6 back to A, and then edge 5 to D. And then after that, you can either take 3 or 4 to C or B respectively, but we're not going to be able to figure things out. Okay, let's try a different path here. So let's try walk number 2 here. So let's maybe try a different tact. So let's start up at C here and see if maybe we can like go top to bottom, bottom to top, and kind of work that way. So what if we went C to A via edge 1, and then down to B using edge 7, and then kind of try to work our way from left to right and top to bottom and back up and stuff. So 6 here back to A, then take 2 to C. But we're going to run into the same issue, right? So this one we're forced to use the edge 3 to get to D, but then we can either go to A or B, but we're not going to be able to use both edges 4 and 5 without repeating something else, right? So again, this seems hard to do, and we're not going to run through all the options because that would be ridiculous. So let's actually see why this is impossible in general. So why can't this be done? So it turns out it depends on what's called the degree of a vertex. So the degree of a vertex in this case, so if I have a vertex, call it V, then its degree is the number of edges adjacent to that vertex, okay? And so looking at our picture again, so first we can look at the vertex A here, and we'll note that around A, we have 1, 2, 3, 4, 5 edges going into it. And so the degree of A is 5. It has 5 edges touching it. And then the rest all have 3, right? So the degree of B is 3, degree of C is 3, and the degree of D is 3. And so what's important about all of these numbers in this case is that they are all odd. So why does oddness matter? Think of it this way. Suppose we actually found a path that went from A to D in the end, okay? Then in that case, every edge that went into B or C had to also have another edge leaving B or C, right? Because we didn't end up there and we didn't start there. And so every time we went in, we also came out so that we could end up going to D. This means that the degree of anything on the interior, basically not your starting point or end point, so here, B and C, would have to have even degree, right? If you go in, you must go out. And this works for everything except for the start and end because you're kind of lopsided there, right? If you start somewhere, you potentially only have to go out once, and if you come back in, you could go out. But you could have one more out than you do in, and thus you could have an odd number total. And the opposite is true for your end vertex. And so here, since all 4 of them are odd degree, none of them could be these interior vertices. They all would have to be starting and end points, but that can only be 2 of the 4. So this is impossible, okay? So our general proof here, I say this in quotation marks because we don't really have the formal language to like prove this very rigorously, is that, again, any vertex that isn't your starting or ending point has to have even degree because every time you enter it, you must also leave it. And since no edge can be used twice, those are different edges each time, so they basically always come in pairs, and thus there must be an even number touching those vertices overall. And so with Konigsberg, right, all three except for A, which has 5, all those are odd numbers, and so in this case, it's impossible to have such a walk. Pretty cool. So, this was back in the 1700s, and graph theory now can be used for much, much more advanced things, and we know a lot more about them. But this is actually the start of an entire branch of mathematics, and by a very, very famous mathematician as well. So I thought it was a cool story to talk about. And so we'll finish with just a little practice on using the ideas that we've talked about. And so I'll give you an exercise where you have to determine if it's possible to do such a walk on these two graphs. Okay, so given these two graphs here, call them G1 and G2, I want you to utilize what you've learned here to determine if either has a walk that uses each edge exactly once. So you'll notice in both cases, you don't have all of the vertices odd, but think if you can use similar ideas to determine if it's going to be a yes or no here. All right, thank you for watching.